Okay, this time. So we are very happy to have Lucien here from King's College speaking on exact Schwinger perturbative renormalization. So Lucien, you have 1 and 5. Please go ahead and people just ask questions if you want.
Great. So first, thanks a lot for the invitation. So I would like to start by a disclaimer, which is that I am not at all expert in string field theory, and so this is not a string field theory talk. But it seems like this topic is of interest for the community, so I'm glad I can share a few ideas with you guys. It seems like also, so another thing is that I am not an expert on this kind of topic. Me and Steve Abel, we've kind of jumped into that field a little bit randomly because we were thinking about other things related to cosmology, and we ended up getting interesting into in functional renormalization. And it turned out that we tried to basically, get a feeling of what's going on in the literature and understand a little bit basic concepts about it. And then we ended up doing our own thing on this specific topic, which is the Schwinger proper time formulation of this functional renormalization group flow. And so I'll try to just maybe guide you through my motivations in this about this story, and then go step by step throughout what we've derived. And yeah, and please feel free to give me any feedback, because we're definitely looking for feedback on this, because we were not in that field initially, so it's good to have some opinions of people who are a little bit more expert than we are on this kind of topics. So yes, so let me start by a few general statements. I'm sure I'm not teaching anybody anything when saying that once you take a scalar theory and then plug it inside the path integral, then in principle you're able to basically include all the quantum corrections to your quantum field theory and obtain an effective action, which, because it's a Legendre transform, has the nice property of giving you an effective potential which is supposed to be convex, and therefore has only one global minimum. So this is a situation which is of interest in field theory, even in particle physics, cosmology, beyond the standard model physics, because people play a lot with scalar potentials. And in the context of the Fast vacuum decay, obviously, if you take a potential at the classical level, it doesn't have to be convex, but one knows that once you include quantum corrections to it, in principle, you should go towards convexity. And so it's a little bit a question in the field to know what is the appropriate potential to use when you start discussing the tunneling of a scalar field from a metastable vacuum to another. So in principle, once you obtain the effective potential for your theory, you should have something which is really convex. But people don't really play with that, because you cannot do anything with such a convex potential, and this is thought as basically some potential which has many possible superpositions of the two minima. Another situation in which non-convex potentials are used is cosmology, and I'm here flashing an example in the production of primordial black holes in the context of inflation. So if you are not familiar with it, inflation is a scalar field theory of the early universe evolution, in which a scalar field is rolling down a potential, and when it is at very large energy, basically it feels a lot of friction, and you're able to enter a so-called slow roll regime, in which the field rolls very slowly and triggers a sort of accelerated phase of expansion of the early universe, in which the scalar field behaves basically like a cosmological constant. And so in the most simple models of inflation, people use all sorts of potential, but the most simple ones could be the quadratic potential or other potentials, although you have to, of course, confront predictions to observations. And recently, people have been playing with potential with have features, especially towards the end of inflation, in order to basically produce cosmological perturbations on specific scales, such that you could maybe produce objects like primordial black holes. So basically, a lot of perturbations at the same scale, so can lead to gravitational collapse on those scales. And if those perturbations are large enough, and then you might be able to have a dense enough perturbation that they could form a black hole. So this is something people play a lot with in cosmology, early universe physics, trying to produce, for instance, primordial black hole dark matter by just having the inflaton field going through this little bump, slowing down a little bit more around here, and then producing all the primordial black holes you want at the mass you want. This is somehow a tool of model building that people use quite a lot. Now, it's been realized in the literature that quantum effects are particularly relevant in that area because the potential becomes particularly flat, and quantum diffusion is important to take into account when you describe the quantum fluctuation of the inflaton, the ones which are responsible for generating more and more perturbation on the same scale around that particular scale. And so people come up with some ways to address this quantum diffusion, in particular using the so-called stochastic inflation formalism, in which people do coarse grain the scalar field theory on a volume. Basically, you think of the Hubble volume as a typical volume in cosmology, which evolves with time. And so people like to use a coarse graining of a field theory on such scales to try to understand, statistically how the field fluctuates over several Hubble volumes. Yeah, my slides are a little bit disorganized. Wait a sec. So let me jump here. So that's the same picture here, the inflaton rolling, producing the CMB modes at relatively high energy, and then meeting this little feature. So people use quantum diffusion as a way to try to deal with quantum corrections relatively accurately in cosmology. But one thing which I always found a little bit striking is that although you address quantum diffusion problems along the inflation trajectory, people never question how the actual shape of the potential may be affected by coarse graining. Once you coarse grain a field, in principle, your theory may be evolving because it becomes an effective field theory. And I think that's a kind of discussion which could be very important for cosmology, and that's where we came from initially, although we ended up not really focusing on that point. But I'm giving you this as a motivation because I think effective field theory in the context of scalar field theory in cosmology is very important. In the context of Fals vacuum decay, what happens is that one is looking for a scalar field which sits in a Fals vacuum and tunnel into a true vacuum, forming double wall configurations of so basically a field configuration in space, which is in the true vacuum in some region inside the bubble, in the Fals vacuum outside the bubble, and this bubble is expanding to the speed of light in the vacuum. And of course, the shape of the potential is extremely important because you need to basically find or calculate so-called bounce action, which tells you basically how you can interpolate from one minimum to another. And this has plenty of implication in early universe cosmology, but in gravitational wave physics, in the context of the electrolytic vacuum, knowing whether it's stable or not. So all the exact shape of the potential that you need to use to make a Fals vacuum decay calculation is very important. Okay. So that was a brief introduction to try to motivate why in cosmology in particular, quantum effects are important, although you may want to describe physics with a classical field theory. That length scales and energy scales matter a lot because in cosmology, those things evolve a lot. The Hubble horizon is something which is varying really significantly over orders of magnitude, the energy scale as well. But in most situations, people just, play with a simple little classical potential, do a little bit of physics with it, obtain some predictions. Whenever we are aware that quantum corrections should be in principle included and maybe important. So is one of the puzzles is to know whether this is a consistent picture, because including in cosmology, although the energy scale varies over orders of magnitude, people usually just take the fixed potential and don't discuss whether that potential is actually moving with the energy scale or with expansion, which I think is a problem. And but it's a complicated problem, so that's why people tend to ignore it most of the time. Okay, so that's where I came from and why I got interested into this story of functional renormalization group flow equations. And so let me give you a little sense of what this looks like, although I'm sure plenty of people are already familiar with it, but I think it's good to have a little review. So the idea is that you may want to coarse grain theory, meaning that you simply average a field over a certain region. So say you're fixing a wave number k, that's the typical wavelength, and you decide to coarse grain your theory over that scale. And so Lucien, Heurtier, and other people have, over the years, since the 90s, developed a sort of strategy to understand what is the effective field theory in which this average field is living. And the technique is the following. Basically, people take the classical action and add to it a piece which is supposed to regularize your action, sort of contribution to the propagator. This delta S here. Forget about the indices here. You may have a bunch of fields if you want, but think about only one scalar field. So that's basically just a volume factor times a regulator times the field square, which contributes to the propagation of your field. And with this extra piece, which is now k dependent because it has the regulator in it, you define this sort of average action. It's not at that point, it's not really average. At that point, it's just the action plus a classical piece, which is k dependent. But then you plug that in your path integral, and you can then define your effective action gamma. So yep, so sorry, there are mixing up notations here, but whatever. So once you plug in the effect in the path integral, you can define your effective actions gamma. But because you know that's the little trick in the Heurtier procedure, because you know that you have added an extra piece to your action, somehow you want to remove it from the theory at the end. So you define you take a classical action, add a piece to it, then calculate your effective action, and at the end say, oh, actually, by the way, I forgot to that I had added a piece, so I need to remove it, and to recover the effective action, which really comes from my classical field theory. And so once you do that, then you can obtain a flow equation for your effective action, and that's the nice element, which is that, and t is the logarithm of the cutoff k. So t and k are basically the same thing. But you obtain a flow equation which tells you how is your effective action evolving with the size of the coarse graining. That means that you may start with a classical field theory, say at k goes to infinity, so no coarse graining at all, point like physics. And then slowly you increase the size of your coarse graining, meaning that you are integrating out more and more fields in the UV, and your IR field, your heavy modes are large wavelength modes are living in an effective field theory, in which the UV mode has been integrated out. So this is nice because then you can start with your classical potential at large values of k, and then scale down run down your flow equation to obtain how is your effective potential evolving from the classical limit to the full quantum effective action. Here, the stress is an integral of a momentum. This is the this is the second derivative of the action. And this is your regulator here, which need to satisfy certain properties such that you recover your full theory without regulator when k goes to 0, and such that you can run down your flow equation smoothly. This you can also interpret this flow equation as a loop, as a one loop result, which is a nice property of it. That Heurtier team like to advertise. So it has a nice little quantum field theory interpretation to it. And so that's something that people have been using quite a lot. However, you will not see a lot of papers which actually can just take an effective potential which is not convex and run it down and obtain something convex, for reasons that will become maybe clearer in what follows. Now, this procedure was used relatively recently by Gina Kroon and collaborators in the context of false vacuum decay, because they realized that the decay of a scalar field which tries to tunnel through a barrier may not be affected by all the wavelength accessible in the quantum field theory. As you can imagine, the bubble has a finite size. The barrier, the potential barrier, also has a finite size. So it might be that relatively short wavelength modes contribute to the process of tunneling, but very large wavelength mode, which are completely beyond the typical size of a bubble or the typical size of your barrier, have no reason to really affect a calculation. So what those people did is that they kind of added by hand in the regulator a way to only integrate out modes which only may contribute to the process of scalar field tunneling. Now, this is not extremely nice, because that means that you put by hand in your flow equation something which cuts off your theory at for given field configuration, that somehow renders your flow equation not very nice to use, so it's a little bit of cooking in there. And so we were wondering whether there was a way to describe this kind of thing in a better way. And it turned out that the Schwinger proper time regularization actually worked pretty well, as you will see. Now, another little caveat of this way of regularizing of coarse graining the theory is that this cutting momentum of order, fixing a cut of k and then cutting momentum of order k is a good idea for modes which are massless. But when a mode actually has a mass, it doesn't really make sense because the energy is given by p squared plus m squared, and so therefore fields which are very heavy but do not have a lot of momentum, in principle, could be cut off as well. And this is something which is nicely encoded in the Schwinger parametrization, because once you rewrite your propagator, which contains p squared plus m squared for a massive field, in principle you end up with this t parameter. And what we thought is that it might be a good idea, if you want to make sure that you cut off all propagators in which particle propagator is more energy than a certain cutoff, then you might, instead of having a regularization on the momentum p, then you may actually want to regularize the theory using the t parameter instead. So the idea we came up with, and we realized later on that actually it was not a new idea, and I'm sure maybe some of you already know about this kind of technique, is to regularize your propagator, but using the t parameter as a variable. So the idea is to here insert this g of k function, which plays the same role as this rk function that was in the Heurtier equation, and just insert that in the expression for the propagator. Now, if you choose a regulator which cuts t as a certain value, typically 1/k squared, then you know that all the propagators in your theory, if you regulate them always in the same way, will basically, regardless on the mass, be cut off as soon as the energy of the field propagating is above or below a certain value of the energy. So to have something which is meaningful, you need, of course, to impose some properties on your regulator, and in particular that in the limit where k is very small, then g has to be equal to 1, such that you really preserve. Sorry, that you I think yes, that you preserve fields. Sorry, that you really coarse grain your theory on small scales, and that's one you don't want to affect. But on large scales, on the opposite, you want to completely to not take into account those modes. So that's why you need to input that it is 0 in the large k limit. Now, in the small k limit, also you may think of it like as saying that in the small k limit, that's where you want to recover your full quantum theory. So that's where you want the regulator to somehow disappear. So that's why it has to be equal to 1, because then your propagator becomes the regular propagator and you recover your full theory. Whereas in the k to infinity limit, you want your classical theory to hold. So you basically want to kill any kind of loop contributions to it. That's why you basically kill your propagator. As I said, this was not a new idea. This has been used in the literature. But what we realized is that there was no flow equation, exact flow equation, which was derived in the literature using that kind of regularization. And so the goal of that talk and of our paper was to see whether we actually could obtain an exact flow equation to obtain the full effective action for scalar field theory. Okay, so an example, just to visualize the effect, but this is quite obvious. If you take a Heaviside function for the regulator, you obtain this kind of propagator, and you see easily here that this exponential factor, basically, if p squared plus m squared is much larger than k, then that kills with exponential, and if p squared plus m squared is small, then that will kill the propagator, which is what we want. Okay, so the idea we came up with, which is relatively standard procedure, but which is very useful in our context, is to write the partition function. So you take a scalar field theory, you isolate the free propagation from the interactions of the field. So this is just a scalar field theory. Okay, no other fields. And sorry, those for convenience, those brackets here will just denote space integration, space-time integration in Euclidean space. And what you do is that you say, well, okay, I usually, if I want to have my full partition function, I can just have my free partition function without any interactions. And I can see then the full partition function as the free partition function on which this operator here, which is an operator with derivatives with respect to the current, is acting. And so what we said earlier is that we want to regularize our theory by basically regularizing propagators, because those are the things which will come and run in loops. So we thought what we can do is to actually regularize our theory only in the free propagation, and then just by adding interaction, having this regularization somehow propagating in the quantum in our quantum field theory. So what we will do is that we will just regularize the free propagation of the field, and then add interactions by applying this operator. So that's our prescription. Okay, so here is the way it works. Your free propagation can be written in terms of the propagator of the field, as you know. Then you can use the Schwinger parameterization to insert this integral over t inside the free partition function. So you obtain this kind of quantity, and then you regularize your free propagation. So you add this regulator gk of t inside this expression. And because you know that in the k to 0 limit, this gk becomes 1, then you know that in the k to 0 limit, you will recover your free partition function, the real free partition function. And then we define the coarse grain or averaged partition function at scale k as this operator including the interactions acting on the regularized free partition function. So once we have this definition, things are relatively trivial, although it requires a little bit of calculation, but you can then define your average effective action from this partition function, which is just very standard expression. And then to obtain your flow equation, you just have to derive with respect to k. This is the derivation of the log of zk. And as you can see, this is a relatively simple expression at this stage, although then you have to calculate, basically, given the interactions you have, how this will act on this k derivative here, to then obtain the real flow equation. Because at this level, the z functions are a little bit like black box. It's difficult to understand what the equation for the effective potential looks like if you don't write things explicitly. But you can do that in full generality. You can, so those are just definitions that I wrote before. And this is the somehow the preliminary master flow equation. So this is the flow equation for the effective action. And those are expressions which are nothing but derivative with respect of the current of this k function, which I wrote above. This k function is a momentum integral, so that looks a little bit like the trace which appears in the Wetterich equation, just that it has this Schwinger parameterization in it. And then you act with the derivative d over dj, delta over delta j, acting once or twice on the k function here. And you have this v, which comes from the interactions in front of it. Those brackets, again, are some space integrals. So sometimes I write x or x, y. That means there are some one or two integrals of a space-time. So now that looks all right, although you may say, well, this is not extremely elegant at this stage. But another aspect of it, which is not so nice, is that you may see that this v here, which I took to be the v, sorry, it misses some indices I, because that's for the interactions, but this v here is in principle the classical potential. So in some sense, it's not so nice, because on the left, you may hope to have a flow equation for your effective potential, but on the right, you see that you have the interaction potential at the classical level. So it's not really a flow equation in the sense that it's just it has on the right-hand side a classical quantities, which is not necessarily what we want. Another thing which you may wonder what it should be in full generality is this mass here. This mass here is only defined in the vacuum. If you are frankly away from the vacuum, let's say on the top of a bump, for instance, in a spontaneous breaking or symmetry breaking potential kind of thing, then this m square here doesn't really make sense, because locally, once you're around the field value, which is not at the minimum, the mass of the field is not the mass in the minimum. So we need a way around it. Although, sorry, I'm going a little bit too fast, because first I should have mentioned that you can always simplify this expression by taking a field, an homogeneous field across space-time. So then you may simplify really your expression by saying that this average action is proportional to the volume times the effective potential. But again, that's what I said earlier. You will have a flow equation for the effective potential with, on the right-hand side, classical potential expressions and masses which are only defined in the minimum, which is not great. Now, it's important to realize that actually the fields that appear as an argument of those potentials here is not the same as the field on the left, because in principle you obtain this field phi k by taking derivatives delta over delta j of this potential here, or more generally, if I go back, sorry, yes, the derivative with respect to the current of the regularized action, not of the full not of the full, sorry, partition function, not of the full partition function without regularization, the one which is regularized, so the one which is coarse-grained. And that means that, in principle, once you derive your effective action, you obtain the coarse-grained field. And which means that the one that the argument phi that you had on the left, which was supposed to be the argument of the effective action, is not the same as the one that you have extracted from the regularized partition function by taking J derivatives. So we came up with this idea that you may define different quantities, phi and phi k, or J and jk, which are the classical solution of the equation of motion in a coarse-grained theory. So we would call, basically, if you use the partition function as a function of J, which is the one where you started with your classical action plus added a regulator, and you take derivative with respect to J, then you will obtain phi k. Now, if you start with your effective action gamma k as a function of phi, and you take it as with derivative with respect to phi, then what you will obtain is jk. It's a sort of coarse-grained current in the space of currents, if you want. So you have to make this distinction to understand what's going on there, and then starting from there, you may say, well, okay, then now I worked at the coarse-grained scale k, and then I want to know if I keep coarse-graining it, how my flow equation will evolve. So what we did is that we actually started with a coarse-grained theory. So at scale k, then we have an effective action k of the current jk. Then you can write this, because it's jk now, not j anymore. We can write this as a path integral of the action as a function of phi plus jk times phi. It's a little bit of gymnastic, which requires thinking about it a little bit, but I think it makes sense. And so in the end, what you can do is somehow define interactions at scale k, and using this effective action as scale k as a starting point, and then figure out what is your flow equation at that scale using this effective action to start with. Then if you want to be away from the minimum, what you can do is to use sort of background field methods to not work out your quantum correction in the minimum, work them out around a point across your potential. So you can basically decompose your field as the classical equation of motion, solution phi bar plus some quantum corrections, and then expand your potential and figure out what is the mass term in that theory, and that will become your second derivative locally, which makes total sense. And if you do that, then what you obtain is a very similar flow equation to what we had before. So where we have basically substituted the interactions that we had before, being the classical ones, by the interactions now in the effective field theory average at scale k. So the V becomes a UK second. And similarly, the master in the exponential now in your propagators is given, because we use the background field method, by the second derivative of the field locally. And what's also nice, once you go through that procedure, is that you realize that your flow equation simplifies quite a lot. And so once you are in the LPA approximation, your field is homogeneous, and you neglect higher derivatives, then you obtain this flow equation, which is really our master equation. Okay, it contains the regulator, the derivative of the regulator, and then the third derivative and second derivative of the field, and that's just this box here. Okay, and then you may, and that's a flow equation now, which is on the value of the derivative of the field, because if you basically want to understand locally how curvature, how the slope of your potential will move. That's the way we found was more convenient to formulate the flow equation and handle it numerically. But it doesn't matter really, because in the end, if you get the first derivative, you just integrate it with respect to phi, and then you obtain the value of your effective potential. So that's it for the flow equation. And then we were wondering, okay, it's great, we have a new flow equation. So first, an interesting comment I want to make, and I do not have actually a real justification for it, but what we realize is that it is remarkable that this flow equation actually corresponds exactly to the one loop result that people had obtained using Schwinger parameterization in the past. So somehow this makes us feel confident that this equation is correct. But now what we have demonstrated is that it's not a one loop result. Actually, it's an exact result at all order. Because we did not use any kind of perturbative expansion on the parameters or interactions when we derived that equation. Now, if you compare to what other prescriptions for obtaining the full effective field theory, like the one that Lucien, Heurtier, and all the people using that kind of technique use, what is the difference with ours? It appeared to us that actually most of the regulators, so if you write down the flow equations, for us, it looks like this. It looks like the derivative of the flow of the first derivative contains the third derivative time of function, which depends on the second derivative of the field. And this function is an exponential. But if you look at, actually, I should have pasted them here, which I didn't. But the most standard regulators that are used in the literature by Heurtier, Lucien, and collaborators is actually not an exponential. It's usually going like 1/1 plus this ratio to a certain power, meaning that if u second becomes negative, 1 plus u second over k squared may become 0, and you may hit a pole when u second is over k squared. So that's why you don't see a lot in the literature people taking a non-convex potential and running the flow equation to obtain a perfectly convex potential. Usually you see plots where you see the potential becoming just a little bit more convex, because at some point people hit a pole and you have to do extra work somehow to make sure that you can smoothly go to convexity. And in our case, we realized that you can basically cross this region without any problem due to the form of the flow equation, and that's a nice property of this flow equation, I believe. And we tried to apply this formalism to the case of the Faust vacuum decay. So maybe I should pause a little bit, and does anybody have question about what I've explained till now, or comments or criticisms? Feel free to insult me.
So I just had one remark when you said that it's you are surprised to get a one loop result, but in some sense, because you're already using the effective potential in the right hand side, you're already integrating over many quantum corrections. So maybe it's why you just have one loop. Because so the Heurtier equation is the same as the Heurtier.
That's true.
Equation is also one loop.
It's a one loop result. That's right.
So I would say from Heurtier, it's maybe not too surprising that you get something similar, since you will work with a
that's true.
Effective action.
Yes. Yeah, absolutely. Absolutely. So for us, actually, it was more like a safety check, because then when we realized that actually people had worked out this kind of equation before, but not in an exact way, then we were seriously wondering what they actually found, and it turns out it's the exact same.
But so when they found the same, it's also with a k-regulated action, or it's just for the?
That's a good question.
Or it's like with the microscopic actions, they get some one loop equation similar to yours, but you'll get more correction because it's k-dependent or something like this.
I think they really just did a perturbative expansion in their interactions and just kept things at the one loop order to obtain their equation, whereas we saw, but I do not remember exactly what was the regularization procedure in their case. but the idea was very similar. I mean, as far as I can remember, the idea was very similar.
But I guess then if you have the same form, it means that if you were like limiting to what they did, you will directly get what they had. So it's why it's a good check.
Yeah,
also.
likely. Yeah.
So if I can ask something, if
Yeah,
you
of
can
course.
go back to previous slide. Oh, maybe the one before. Oh, no, this one. So this equation. So this is the Wetterich equation, this flow equation.
But actually, this is you could generalize it for Wetterich if you put a different function for this ft function here, I believe.
Okay, so what I don't understand. So this looks kind of like some Schwinger-Dyson equation, but if you want to say that this is exact to all orders in perturbation theory, so you need all correction not only like to the propagator but also to the vertex. And I'm not sure I'm seeing this in this formula. And also I don't understand why you have 3 derivatives on U.
So here on the left, it's the first derivative.
Now I'm looking at the upper formula.
Oh, this one?
Yeah.
Yeah, I mean you can integrate it with respect to phi if you want. You will obtain an equation for u of phi, and then you may not have a third derivative here. We found it convenient to express it for the first derivative because we were using this background field method. So somehow we needed to get rid of the value, and taking the first derivative was simplifying things. But you can integrate this with respect to phi. You will obtain a derivative with respect to k of uk of phi minus uk of phi 0. You can integrate it. That's no problem.
Okay.
But yeah, it's a null order result. Yeah.
So how can it be an all order result? So just
because we did not.
So you had some picture. You had some Feynman diagram type of picture in one of the previous slides.
Yeah, that's the Wetterich procedure.
Yeah, not really
here.
Yeah. Oh, is this
so
thing?
Wetterich has something slightly similar. They have, so here that's a momentum integral distress, and that's an inverse propagator in which you add this regulator, and you have this derivative of the regulator. So the form is not very different. It's just not regulated using the Schwinger parameter. But structure is quite similar.
So what does the 2 on gamma k means? The 2 is a 2-point function, or
that's the
second?
That's the 2-point function. Yeah.
Okay, so the point is that you are studying like some like vacuum energy, that it's that there are like no vertex corrections, no external lags, or
But here you have also vertex correction also, because on the left hand side it's a full effective action with all the vertices. And like if you wanted to obtain the correction to the different vertices, you could just take functional derivative of the left hand side.
That's right.
Then you take off the right hand side and you can get the equation for each vertex at each order. And each vertex will have all the quantum corrections. So it's just that in the trace you have the effective propagator at order k with group corrections. But this equation has much more than the propagator. And it's the same in the equations that are later. You can also extract corrections for all the vertices.
Yeah, that's right.
So this, should I view it like some sort of Schwinger-Dyson equation, not only like for the propagator, but also for all the vertices and things like that? Or?
I would think so.
Sir? You don't think so?
No, I would think so, yeah.
Oh, yeah, here you have also the vertices correction. Like if you could solve this equation, you will get the full effective action at order k, at energy k.
Okay, and what's the relation of this Litton-Wetterich equation to your equation?
So the difference is in the way it's regulated. Here in their way of regulating it, they add a piece to the propagator to kill some propagators at a certain scale. Because if that quantity becomes large, then that will kill that one of them.
Yeah, right.
So that's that's a sort of additional piece to the that you add to the propagator. Whereas instead of doing that, we are really regulating the Schwinger integral.
Oh, okay.
So we are regulating things using the proper time. So you may say this is just a technical difference. It's not there's nothing which is physically. I mean, it's a different way of regularizing. I don't know how to say it in a different way, but it has yeah.
I think one way to say, like in the more string theory language, in the first regulation of Wetterich, it's you take like a hard cutoff, so you would have something, but you just smooth it a bit. And here it's like the stub parameter, so if g of k is a theta function, you just get.
It can be, but it doesn't have to be. It doesn't have to.
Yeah, it's the simplest case to just give the difference. Like simplest case here, it's a stub parameter, just a lower limit on stubs. And in the other case, it would be hard momentum. So it's kind of the two simplest case.
Okay. Okay. Thank you.
Thank you for the questions. So as a I mean, to see how useful this equation would be, what we did is we applied it to the phase vacuum decay calculation, in which you so that's a typical example people can use for the phase vacuum decay in order to obtain thin wall bubble profile. So thin wall means that the wall of the bubble would be very localized, and that's typically what you get when you have a let's say two minima of your potential which are slightly different but almost degenerate. So that's where this little epsilon parameter comes in order to break a little bit the degeneracy between the two minima. And so what Coleman will explain is that you can just write down your action for the scalar field and look for symmetric solutions in Euclidean time, in Euclidean space, and that's the so-called bounce instantaneous solution, which will interpolate between one minimum and the other. And you may want to go and calculate the full decay rate of your metastable minimum by doing this kind of calculation. So there is a determinant calculation which is tricky, and there is this bounce action which is the easy part of the calculation. So what we did is that we tried to take this kind of potential, use the flow equation to see how it evolves, and at every step see how this bounce solution for the action evolves, and how that affects the lifetime of scalar field. So that's the typical calculation you need to do. You basically flip your potential because you're in Euclidean, using Euclidean coordinates, and therefore there is this minus sign in front of the potential, and you look for field configuration which basically roll trying to arrive at infinity on the metastable minimum here. So you can use a sort of shooting method where either you try to find out what's the initial field value you need in order to arrive at infinity in the sky at the minimum here, and then you will obtain this kind of bubble profile. And from the bubble profile, you can already you can look at its structure, see whether it's thin wall or thick wall, that's all I need to say about this. So that's what we did. So we started with a potential, with a classical potential, which is the blue dashed line here, and we tried to see how it evolved using our flow equation. And what we noticed is that using the equation I showed earlier, depending on what scale you start, basically your potential has more or less time to run towards a fully convex potential. But there are some cases where actually it ends up freezing. And those cases are basically cases where your potential is not yet fully convex. Once the typical mass scale of your field crosses the threshold, the cutoff k, at which you are at that point. It's a little bit puzzling because in principle you would hope that that taking a non-convex potential, you would run down your flow equation all the way to k equal to 0, and then you would obtain a potential which is completely convex. But we have to keep in mind that in the flow equation we have derived is in the approximation where we only looked at completely homogeneous scalar fields configuration, and so we interpret this phrasing as an indication that we have not included at all in our theory field configuration which are not homogeneous, such as the bubble configuration. However, the way we interpret this qualitative difference between those two cases is that in one case, even though you would ignore completely non-homogeneous field configuration, you would see that if you include more and more quantum corrections, your potential will become completely convex, and that sounds to us as saying that you will never have a first-order phase transition using such a potential, because there is no reason for your field to be trapped in a minimum if the effective field theory in which it's living does not have a metastable minimum at all. Whereas in that case, you will say that if you only consider field configuration which are homogeneous and you include more and more quantum corrections to your field theory, in principle, you can see that at some point you include more and more quantum corrections, but that is not affecting at all the shape of your potential anymore. It is not convex. It is what it is, and in principle, you can do some physics with it. And in that case, you can be confident that that you are using a potential which is meaningful, because you can see that adding more and more quantum correction to your theory is not actually changing the shape of your potential. Now, indeed, if you would keep including and say, well, actually now you're supposed to form bubbles, and in principle, adding those bubbles that are your potential will become convex, then you may reach perfect convexity. But we think it's probably a good idea to wonder whether you can have a homogeneous field configuration stuck in a metastable minimum at that level. And our prescription is to say, well, if your potential runs into a convex potential using only homogeneous field configuration, then no chance that you have a first-order phase transition. But if you actually see that your potential freezes when it is still non-convex, then likely what you need to say is that, well, at that point, my homogeneous scalar field is stuck in a metastable minimum, and here's the shape of the potential that I should use to do any kind of calculation for my false vacuum decay lifetime calculation. So doing this, you can somehow scan over parameters and see that sorry, I should explain a little bit what this plot is. So that's the x-axis is basically the scale k with respect to the mass of the field in the minimum, and the different curves here represent the solid lines, represent the width of your bubble, and the dashed lines represents the total radius of the bubble. So what you see is that when you start at large k, so you're in the classical field theory, you start in a limit where you have a metastable minimum, and we are using this potential, which is the typical fin wall, which gives you the typical fin wall profile for your bubble. So on the right-hand side of the plot, the width of the bubble is always much smaller compared to the radius of the bubble, and that's normal. Now, what we see is that you run down your theory, and you see that this width, take a given color, you follow this line, the width is increasing, and you may, and similarly, the radius of the bubble is, oppositely, the radius of the bubble is decreasing, and the two match at some point. The two meet each other. That means you're basically reaching the limit where your bubble is not thin wall anymore. It's thick wall. And what happens is that in the case where those two meet, before the scale of your cutoff has become comparable to the scale of the mass of the field, then basically your potential becomes fully convex before it freezes. And in that case, after it becomes convex, then there is no point calculating a tunneling rate anymore. However, on the opposite case, where the potential keep running, and the width of the bubble never reaches the radius of the bubble, you see that at some point, once they cross the line where, which is the line 2 pi over k, basically the wavelength, your cutoff corresponds to wavelength, which is of order, for instance, the width of the wall. From that point, you see that the potential freezes. So as soon as if the width is able to cross that black line, basically then that means your potential has been freezing before it was convex. And in that case, you know that you can keep running down your theory towards zero. Potential is not moving anymore, and it makes sense to calculate a phase vacuum decay there. That's our prescription. And it's remarkable to see that basically this freezing happens when the crossing between the plane line and the dot and the dashed line happens before or after the black line. If it happens before, no first order phase transition. If it did not manage to happen before, then your potential will freeze, and those lines will never meet, and then you can claim that there will be a first order phase transition. That's our conclusion here. Okay. Now we've not pushed the thing forward too much, but we believe that the way we have derived this flow equation actually could be applied to more general theories, and we don't see any obstruction for our flow equation to be derived, including other types of particles, including fermions, for instance. So in the appendix of our paper, we also proposed a solid flow equation, including fermions. It's not pretty. Right? You may go through the derivation and see that. So you can do the same, and you can have the partition function for currents, fermionic currents. You can regularize fermions in the same way that you regularize scalars, and obtain a fully general flow equation for your effective action, the full effective action, including scalar fields and fermions. It's not very pretty, but it's understandable. I mean, it's understandable, and those are just space integrals of quantities, which include the interactions as before, between the scalars and the fermions, and you may obtain a flow equation for your effective potential if you want the effective potential for the scalar field. Well, you may actually derive a flow equation for it, which now depends not only on the third derivative of the effective potential with respect to the scalar, but also on the Yukawa terms, which somehow is a nice generalization of the previous results. It's still somehow a one loop result, but now including Yukawa interactions. Now, it's not obvious how to use such a flow equation, because you'd probably need to run several differential equations, and there might not be a finite number of them, if I remember well. So we've not pushed the story too far, but I think it's interesting to see that we could get flow equations for theories which are more general than just scalar field theories. And that leads me to my conclusions, actually. So Schwinger parameterization provides a good way to obtain a meaningful coarse-grained theories, and in which you can do physics, at least at the relatively naive level, trying to run down the theory, starting from the purely classical theory all the way down to the full effective theory, including quantum corrections. It is not relying on any perturbative expansion. It is an exact equation. And it benefits from this smoothness property, that you're not hitting any pole when you are running down your theory all the way down to k equals 0. And as you could see, it is easy to apply it to physical situations, such that the phase vacuum decay now, it's ongoing work to understand how it could be applied to other situations like cosmology. And I think that's a very exciting directions, because you may realize, if you look into the literature on stochastic inflation and a lot of situations which involve coarse-graining, that the potential is always considered fixed in those kind of contexts. So somehow that you coarse-grain your theory, but you forget about the fact that coarse-graining may actually modify your effective action at a certain scale, and that's something I'm starting investigating at the moment with people at King's College and Durham University. So if you are interested, feel free to contact us, and we'll definitely be happy to also help you understand how the paperwork, how this flow equation works. Thank you very much.
Thanks a lot, Lucien, for the great talk. So like always, we have see if people have questions now, then I will stop the recording and see if people have more questions of recording. So has anyone questions? Carlo, you want to say some questions?
Yes, one more. Yes, yes. Hello.
Hey.
Hello.
Do you see me? Hello.
I cannot see you, but we can hear you.
My computer is not working. I'm sorry. I think I have some problems in the but okay. I hope you can hear me. I mean, it's a very general question. So I don't understand. Okay, is it conceivable that with this method you can also get some idea, or I mean, you can also capture non-perturbative contributions to the effective actions, and
Yes,
not just the perturbative series?
Yeah, no. So that again, I insist on the fact that there is no perturbative expansion in that in those derivations. This is not specific to ours, and the Wetterish calculation is also non-perturbative. So, so you can consider non-perturbative situations using flow equations like that. There is.
I see. So this is not based on a, let's say, on a Gaussian evaluation of the path integral.
No.
Okay. Thanks.
You're welcome. I think that's why this kind of flow equation may be useful in a lot of situations. Non-perturbativity appears all over the place. So if we are able to describe the full effective action, including non-perturbative correction, that would be great for a lot of physical situations.
Mm-hmm.
Sorry?
If I can ask something. Okay, so in the usual approach to quantum field theory, we have some ultraviolet Lagrangian with couplings, with masses, etc. So we have some parameters and degrees of interactions, etc. Where are all these things hidden in gamma? So there seems to be no information about some underlying theory. So it seems to me to be completely general. So how can you get something meaningful out of this?
Okay, maybe I should go back to the definition of gamma is when I'm not sure to which level you're asking this question.
The Wetterick equation, But
that Wetterick equation is really giving you this effective action gamma, the usual one, right? So your Lagrangian is Lagrangian. You start with a classical Lagrangian.
Yes.
So that's where your interactions are going.
So the information is hidden in the boundary condition. So you have a flow equation and you need some initial conditions, and the initial condition is a microscopic action you need to start with.
Right.
Oh,
so
I see.
Okay.
So that's
yes.
at t. That's at t equals 0, or
yeah. So the thing is, you can in principle, naively, you would say, okay, at k to infinity, I start with my classical theory. But classical k to infinity doesn't. I mean, you cannot even numerically do that, right? So you need to start at some UV scale, and that's where you would. Is that what you're saying, Aaron? That's the boundary condition you start with, right? You start with a theory which has certain parameters in it at a certain scale, k UV, if you want, and you start from there. And now you say, well, now I'm going down in energy. So you say, even geometrically speaking, you may say, well, I start with a certain resolution on my grid. You know, like I'm going to coarse grain, but I start with a finite resolution. before I start coarse graining on larger and larger scales, I start with a theory which I think I know at a certain scale. If that makes sense. And then you say, well, okay, now say that I know my parameters at this UV scale, meaning this little tiny pixel size. Then how, if I coarse grain more and more, how is that affecting how quantum corrections are affecting my scalar field theory? Or my parameters evolving? Does it make sense? Is that answering your question?
Okay. Yeah, thank you.
What's the question I know? Is the analysis strategy required?
But so if I can comment on the question from Carlos, so it's also why I was interested in your paper. It's because it's kind of a generalization of the stub cutoff we use in string field theory. So the hope would be that with this equation, we could try to get some more non-perturbative information on string field theory in some way, if we could, you know, extract data from this equation.
Yeah, but that is precisely why I asked this question, because at least the way I understand this deformation in string field theory is very perturbative, and it comes out from a perturbative expansion of the path integral. So I was wondering how essentially what is the role of classical solutions that are, let's say, quite far from that are not captured by the saddle point approximation around the perturbative vacuum. And yeah, so as far as I understood, is sort of hidden in these formulas in a way that I would like to understand better.
Can I ask a question?
Yeah.
Yeah. So say that you have this differential equation for between t equals 0 and t equals 1, and t equals 0 is your UV and t equals 1 is your IR. Does it meaningful to talk about t smaller than 0? Like what happens if you push it further, just formally? I know physically it doesn't make sense in the situations that you're talking about, but you know, is it possible to talk about that differential equation in that regime?
I'm trying to wait a sec. I'm trying to understand what you mean by t equals 0, because
yeah, so what I'm saying is that for example, yeah, so you had this flow equation, right? This decay, and the range of k is from infinity to 0. That's
that's right.
Is that correct?
Yes.
So what I was imagining is that say you put this conformally to between 0 and 1 and try to evolve it even further, smaller than 0. Is it even meaningful to talk about that? For example, is it meaningful to talk about the negative Schwinger parameter? Because that's what will correspond here.
Naively, I would say that if you do, I'm wondering whether there is a sort of, because U-second in our case can be negative.
Yeah, then that's correct. Like, but for example, that happens in string theory too. Like, if you have a tachyon, that's just basically infinity, but then you can do some analytic continuation to get rid of that.
I'm not sure what about this too much. I don't see an obstruction. Yeah.
Okay. Yeah.
Yeah.
No problem.
I don't see an obstruction in principle, but I need to think about it more, because I'm not sure. So if naively, I would say you could imagine bringing k to negative values, if that's what you're saying, or to prolong your integral to minus infinity to infinity.
Yes, I'm saying something along those lines. But maybe they are distinct, but both cases are certainly interesting in string field theory, at least. but
you
physically it doesn't make sense.
UV-IR connection kind of thing, right? Something like that you're trying to get into.
Yeah, I mean, problem is that even your UV theory in string field theory is kind of like effective theory, like there are infinite couplings, and so it is a question if it is like say that you can analytically continue your flow equation to those negative values and run it, maybe you will end up with something different than that. So that was the motivation behind this question, but I am not sure.
Okay.
Mm-hmm.
Yeah, I need to think more about this.
Okay, thank you.
Yeah, another way to say what Atakan was saying, so something we encountered when we are trying to understand better the quartic interaction is that in string theory, string theory, the amplitudes and vertices are described by a moduli parameter. So you iterate over a position of points on the sphere. And when you write the string theory, you have some contribution which are described by 3-point interaction connected by a propagator. And here the modulus is a Schwinger parameter. And what we were seeing with Atakan is that it looks, I think it's Ashok who suggested it first, is that you could describe also the 4-point interaction with negative stubs, also negative Schwinger parameter. So it's what we are trying to understand, but for now we didn't really find.
Yeah,
and I think Atakan has other motivation also from other things, but it was one way to see why we could find negative values.
Yeah, important thing here, for example, is that the T for us is complex. And we are integrating over the disk. Like there is this complex twist part. So certainly, like if you're talking about taking, for example, K to be complex as well, it might be possible that you can analytically continue this differential equation to the non-physical regimes and try to get some leverage out of it.
Might be, yeah.
Sorry, can I ask, Atakan, why do you want to continue to the complex plane? What do you expect?
Honestly, I have no prior expectation, but my maybe you can cancel certain regimes in the vertex region. That's the the best thing that you can do. But I'm not sure what to expect. It's just an exploration sort of thing.
Okay, thanks.
So do we have more questions for Lucien? Okay, so if not, I will stop the recording and then we can see if we have more questions.